This is Lesson 10 in our Calculus 1 series, Basic Differentiation Formulas. In Lesson 9, we saw the different derivative notations. We said for y equals f of x, we can denote the derivative function by f prime of x, y prime, dy dx, or df dx. And the second derivative, f double prime of x, y double prime, d square y over dx square, d square f over dx square. And when evaluating these at the point x equals a, we write f prime of a, y prime of a, and here we use the evaluation bar dy dx at x equals a, df dx at x equals a. We also saw the differential operator d by dx, which means we're taking the derivative of whatever's inside the parentheses. So we read this as the derivative of whatever's inside the parentheses with respect to x. And this is going to be a very useful notation for us as we go through the basic differentiation formulas in this lesson. So let's start with the constant function, f of x equals c. What is f prime of x? Well, by definition, we know that f prime of x is a limit as h goes to 0 of f of x plus h minus f of x over h. Since it's a constant function, both of these function evaluations are equal to c, and so we're taking the limit of 0 over h as h goes to 0. Now notice, for each different h value, we have a quotient here that is 0 in the numerator and not 0 in the denominator. So each of these quotients is equal to 0. And so this limit is equal to 0. So we have that the derivative of a constant is equal to 0. And that makes sense because remember the derivative is the rate of change, and constant functions don't change, so their rate of change is equal to 0. You could also think of it as a constant function being a horizontal line, y equals c, and its slope is equal to 0, so its derivative should be 0. So this is our first basic derivative rule. Now let's consider the function f of x equals x. We know this is the line y equals x, and we know that its slope is equal to 1 at any x value. So its slope is constant at 1. That tells us f prime of x, the derivative function here, should be the constant function 1. So the derivative of x is equal to 1. And certainly this can be proven using the limit definition of the derivative, and you can find that in your textbook. And keep in mind that all of the derivative rules we're going over in this lesson can be proved using the limit definition. That's where they all come from, because that is the definition of the derivative for any function. Let's take a look at another. This is the power rule. Derivative of x to the nth power is nx to the n minus 1. So for example, for y equals x to the fifth, y prime, the derivative function, is going to be 5x to the fourth. This is x to the n is equal to 5, and so the derivative has 5x to the fourth, nx to the n minus 1. Another example, g of x is equal to x squared, then g prime of x is equal to 2x to the first, or 2x. For h of x equals x to the 1/2 power, the derivative h prime of x is going to be 1/2 x to the negative 1/2. So again, we're bringing that power of n down in front, and then we're subtracting 1 from the power. So this 1/2 comes down in front, and then we have a power of 1/2 minus 1. So that's a negative 1/2 power. And in general, we don't want to write our answers with negative exponents, so let's write this with a positive exponent by bringing that x to the 1/2 into the denominator with the 2. So we have 1 over 2x to the 1/2 here as our derivative. And remember that what we're computing here with these derivative functions are the slope functions for the original. So remember that the derivative function gives the slope of the original function at any x value. So for example, let's take a look at g of x equals x squared. What does g prime of x equals 2x tell us? It tells us that at any x value on this graph, on this parabola, the slope is going to be 2 times the x value. So here is that parabola, g of x equals x squared. And what we found with g prime equals 2x is that the slope at any point is going to be 2 times its x value. G prime of -2 is -4. The slope here is -4. The slope at x equals -1 is -2. The slope at x equals 0 is 0. The slope at x equals 1.5 is equal to 3. For any x value, the slope is 2 times that x value. That's what our derivative function is telling us here. Okay, let's take a look at another derivative rule. This says the derivative of a constant times a function is the same as the constant times the derivative of the function. So if we want to take the derivative of 5x squared, we could pull the 5 outside and take the derivative of x squared, which we know is 2x. So this is going to be 5 times 2x, or 10x. Also, we have that the derivative of a sum or difference of functions is going to be the sum or difference of the derivative of those functions. So for example, if we have y equals 3x to the fifth plus x, we can take the derivative of 3x to the fifth and add it to the derivative of x, and that's going to give us y prime. So y prime here is going to be 3 times the derivative of x to the fifth, that's 5x to the fourth, plus the derivative of x, which is equal to 1. So here we have 15x to the fourth plus 1 as our y prime. Similarly, if we have h of x equals radical x minus 4, remember that radical x is x to the 1/2, so writing it this way helps fit it into our derivative rules. And then taking the derivative h prime, we're going to have 1/2 x to the -1/2 minus the derivative of 4, the derivative of a constant, is 0. And simplifying this term, we get, again, 1 over 2 radical x. And so that's h prime of x. For our trig functions, sine and cosine, we have that the derivative of sine x is equal to cosine x, and the derivative of cosine x is equal to negative sine x. So let's take a look at y equals sine x and its derivatives here. If y is equal to sine x, then y prime is going to be the derivative of sine x, and that's cosine x. And then y double prime is going to be the derivative of cosine x, and so that's negative sine x. And then y triple prime is going to be the derivative of negative sine x, and that's negative cosine x. And then the fourth derivative of y is going to be the derivative of negative cosine x. So that's negative of negative sine x, and we're back to sine x. And so then we know the fifth derivative would be cosine x, the sixth derivative would be negative sine x, the seventh derivative would be negative cosine x, and the eighth derivative would be again sine x. Let's take a look at some more examples. Here we have a third degree polynomial. F of x is equal to 3x to the third minus 4x plus 2. Taking the derivative, this constant multiple of 3 is going to just carry down and multiply the derivative of x to the third. So that's 3 times 3x squared minus, here we have a constant multiple of 4 that carries down, and the derivative of x is equal to 1. Plus, here we have a constant, so the derivative of a constant is equal to 0. Now don't be confused by these constant multiples of a function versus just a constant. We're not taking the derivative of 3 here, we're just carrying down the 3 and taking the derivative of x to the third. This is a c times f of x, and so the derivative is going to be c times f prime of x. Same thing here, we have c times f of x. So the derivative is going to be c times f prime of x. But here, this is just c, and the derivative of c is 0. So here we have 9x squared minus 4 as our derivative. Let's take a look at another. G of x is equal to x to the 10th plus 3 to the 10th. So g prime of x is going to be, here we have the power rule, 10x to the 9th power. And students often get confused by something like 3 to the 10th. They want to say the derivative should be 10 times 3 to the 9th power. But be careful, 3 to the 10th is just a constant. So its derivative is 0. Don't be fooled by that. So g prime of x here is just 10x to the 9th. Now here we have y equals 1 over x squared minus 2 over radical x. And the thing to remember here is that in order to use the derivative formulas we saw above, we have to make these functions fit exactly in. There's no rule that says 1 over x to the nth power and how to take its derivative. The rule says x to the nth power. So in order to take the derivative here, we have to write this as x to a power. So we rewrite this as x to the negative 2, and then we can take its derivative. Same thing's happening here. We have 2 over radical x, but there's not a rule for 2 over x to a power. The rule is x to a power. So we need to get this written as 2 times x to the negative 1/2, then we can use our power rule. So once we have it rewritten this way, then we write y prime is equal to, and then we take our derivative. The negative 2 comes down here, so we have negative 2x to the negative 3. Here we have 2, constant multiple, times negative 1/2, x to the negative 3/2. And then we want to simplify and write without negative exponents. So this becomes negative 2 over x to the 3rd. Remember that this negative 3 power only applies to the x, so this 2 stays up in the numerator, only the x goes down to the denominator. Here we have the negative 2 and the negative 1/2 canceling each other, leaving a positive 1, and we have x to the 3/2 power in the denominator. And so that's our y prime. And if you're wondering why we want to write without negative exponents, it's because when we plug in x values, we have to write it this way without negative exponents in order to make our evaluations. Let's take a look at another. Y equals sine t plus pi cosine t. Okay, the derivative y prime is going to be the derivative of sine t, that's cosine t. Here we have a constant multiple, so we bring that down. And the derivative of cosine t is negative sine t. Make sure you're using parentheses here. I can't tell you how many times I've seen students not put parentheses and then magically this becomes subtraction. Pi minus sine t. I don't want to see any magical subtraction, so don't forget to use your parentheses. This is cosine t minus pi sine t. And that's our y prime. And just keep in mind the notation here, we have t as our variable instead of x. So instead of dy dx, we could write this as dy dt is equal to cosine t minus pi sine t. Let's take a look at another. Here we have what looks like a quotient of functions. We have x to the 4th minus 2x squared plus 1 over radical x. But again, we need to make this fit our derivative rules. We don't have a rule for quotients yet. That comes in the next lesson. So what can we do with this now? The only thing that we can do is separate and make 3 separate fractions here and simplify each of those terms before we go on. So we're going to put each of these terms in the numerator over its own copy of radical x, and then simplify. X to the 4th over x to the 1/2 is x to the 7/2. Remember, we're subtracting 4 minus 1/2 here. And this becomes minus 2 times x to the 3/2 plus x to the negative 1/2. And remember, this is still the original function h of x. We didn't take our derivative yet. Now we can write h prime of x is equal to, and take the derivative. So we have 7/2 x to the 5/2 minus a 2 times 3/2 x to the 1/2 plus a negative 1/2 x to the negative 3/2. And then we'll rewrite this without negative exponents. And so we're here. Let's take a look at another. Here we have f of x equals x plus 5 multiplied by 2x squared plus 1. And again, remember, we don't yet have a rule to take the derivative of a product of functions. So before we take our derivative here, we're going to have to get rid of the product of functions and multiply this out. So please pause the video, take a few minutes, and find f prime of x. So multiplying out, we get 2x to the third plus 10x squared plus x plus 5. And then taking the derivative, we're going to have 2 times 3x squared plus 10 times 2x to the first plus 1 plus 0. And so that's a 6x squared plus 20x plus 1. And that's f prime of x. Let's take a look at this. Where does g of x equals x squared minus 4x plus 2 have a horizontal tangent line? Well, we know when we see horizontal tangent line, they're telling us that the slope must equal 0. So we're looking for the x values such that g prime of x is equal to 0. Because remember, g prime of x gives us the slope of g at any point. So we take g prime of x, we get 2x minus 4 plus 0, and we set that equal to 0. And we solve for x. That gives us x equals 2. And that is where our parabola has a horizontal tangent line. And just keep in mind here, the question said, where does this function have a horizontal tangent line? Whenever you're asked where about functions, you always want to answer with an x value or with the xy pair. So in this case, we would say at x equals 2, or we could say at 2 comma negative 2. By plugging that 2 into the function, we can find the y value of negative 2. So remember, answering a where does this happen is always an x value, or you answer with the xy pair. Let's take a look at another. Where does y equals sine x have a tangent line with slope equal to 1? Okay, this is different. Now they're saying we want the tangent line slope to be equal to 1. That tells us we're looking for the x values such that y prime of x is equal to 1. So let's take the derivative, that's cosine x, and set that equal to 1. Where does this happen? Where is cosine x equal to 1? Well, we know it happens at x equals 0, 2 pi, 4 pi. Also going in the negative direction happens at negative 2 pi, negative 4 pi. So note that we're talking about the even multiples of pi, and so we note that as x equals 2 pi k for k in the set of integers. So k includes 0 and all the positive and negative whole numbers, and so the set x equals 2 pi k represents all of these values for which cosine is equal to 1. And so let's take a look at the graph. Remember, this is the original function y equals sine x, and we want to know where the tangent line has slope equal to 1. So here's our graph of y equals sine x, and these are the points at which the slope is equal to 1. 0, 2 pi, negative 2 pi, etc. Let's take a look at another. Where does f of x equals 2x to the 1/3 plus 1 have a vertical tangent line? A vertical tangent line has infinite slope. So we need the x values such that f prime of x is going to be non-zero over 0. So let's find f prime of x. It's going to be 2 times a 1/3 x to the negative 2/3 plus 0. Simplifying, that looks like this. And we need the x values for which this is going to be non-zero over 0. And so that's going to be just x equals 0. And so f has a vertical tangent line at x equals 0. Or we could say at 0, 1. Let's take a look at another. Find an equation of the tangent line to f of x equals x to the 5/3 minus x to the 1/3 at x equals 27. Please take a few minutes, pause the video, and work on this. Well, we know for an equation of the tangent line, we need to find the point of tangency and the slope at that point. So at x equals 27, f of 27, the y value here, is going to be 27 to the 5/3 minus 27 to the 1/3. 27 to the 5/3 can be computed as 27 to the 1/3, then to the 5th, so that's 3 to the 5th, or 243. And 27 to the 1/3 is just 3, and so that's minus 3 here, and so we have a y value of 240. So the point of tangency is 27, 240. And we know that our slope here is going to be given by the derivative of f at x equals 27. So we need to find f prime of x, that's 5/3 x to the 2/3, minus 1/3 x to the negative 2/3. So now before we can plug in the 27, we want to write this without a negative exponent, and then we can plug in the 27 and make that computation. So 27 to the 2/3 power, again, is 27 to the 1/3 first, that's 3, then take it to the second power, that's 9. So we have 5/3 times 9 minus 1 over 3 times 9. So that's 15 minus 1 over 27, that's 404 over 27, that's our slope. So we have y minus 240 is equal to 404 over 27 times x minus 27. And so we have y equals 404 over 27x minus 164, and that's the equation of our tangent line. Now let's take a look at an equation for a normal line. Find an equation of the normal line to g of x equals cosine x minus 2x plus 1 at x equals pi. The normal line is going to be perpendicular to the tangent line and to the function at that point. So what we're looking for here is to find the slope of the tangent line and then take the negative reciprocal of that. That's going to give us the slope of the normal line. First though, let's talk about the point this normal line goes through. We know that x is equal to pi, and g of x is cosine x minus 2x plus 1. So g of pi, the y value here, is going to be cosine pi minus 2 pi plus 1. Cosine pi is negative 1. So this is negative 1 minus 2 pi plus 1. This is negative 2 pi. And so our point is pi comma negative 2 pi. And our slope, we said, is going to be negative 1 over g prime of pi, because we want to take the negative reciprocal of the tangent line slope. So let's find g prime of x. G prime of x is equal to negative sine x minus 2. And so g prime of pi is equal to negative sine pi minus 2. That's 0 minus 2, or negative 2. And that would be the slope of the tangent line, but we want a normal line, so we want to take our slope to be negative 1 over negative 2. So that gives us a positive 1/2 for our slope. And so we have y minus negative 2 pi equals 1/2 x minus pi. And that simplifies to y equals 1/2 x minus 5 pi over 2. And that's the equation of our normal line to this curve at that point. Now let's talk about distance, velocity, and acceleration. Recall from lesson 8, for a distance function s of t, the rate of change, or the derivative, gives the velocity. And also we have that the rate of change of velocity gives acceleration. So when we have a distance function s of t, its derivative s prime of t, which sometimes we write as v of t, that's the velocity function. And s double prime of t, or v prime of t, or a of t, that's the acceleration function. So here, if a football is thrown from a height of 6 feet with an initial upward velocity of 50 feet per second, the height of the football, neglecting air resistance, is given by s of t equals 6 plus 50t minus 16t squared. So they're giving us a distance function here that represents height of the football at any given time. And we're asked to find the maximum height of the football, and they also want to know what is the velocity of the ball when it is caught at a height of 5 feet. Okay, we're given the height function here for the football, and they want to know what's the maximum height of the football. To find the maximum height, we realize that this occurs when the upward velocity is equal to 0. So we need to find at what time the football stopped increasing in height and starts to decrease in height. At that point, the velocity of the football is 0. So we want to find s prime of t, the velocity function, and set it equal to 0. That's going to give us the time at which it reaches its maximum height. Then we're going to take that time, plug it back into the distance function, into the height function, and get that maximum height value. So s of t we said is 6 plus 50t minus 16t squared. We take the derivative s prime of t, and that's 50 minus 32t, and we set that equal to 0. We solve for t, and we get 25 over 16 seconds. It's approximately 1.56 seconds. Now to find the maximum height, we're going to plug this t value back in the original function. The numbers are a little bit messy, but we get 721 over 16, which is approximately 45.06 feet for the maximum height of the football. So again, to find this maximum height, we first realize that at the time the ball reaches its maximum height, its velocity is equal to 0. So we find this maximum height by first finding the time at which the velocity is equal to 0, and then plugging that back into the distance function, the height function. In part B, they asked, what is the velocity of the ball when it is caught at a height of 5 feet? Well, we already found the velocity function, but when is the ball caught at a height of 5 feet? We have to find that t value first. So we need to find the t value for which the height is equal to 5. So we have to set this original function equal to 5 and solve for t. First, we have to find the time at which the height is equal to 5 feet, and then find the velocity at that time. So we set the original function s of t equal to 5. We simplify, we have a quadratic, and we use the quadratic formula in case it doesn't factor. And we get t is approximately 3.145, or t is negative 0.02 as our two solutions to this quadratic. So note that this negative time value doesn't make any sense. That talks about before the ball is even thrown, so that's not the time value we're looking for. We're looking for t to be approximately 3.145. And so that is the time value that we plug back into our velocity function, because we want to know what's the velocity at this time. This is the time at which the ball is caught at 5 feet, and we want to know its velocity at that time. So we plug it into the velocity function, and we get approximately negative 50.64. And so that says the velocity of the ball when it is caught is approximately negative 50.64 feet per second. And this negative is just indicating that the height of the football is decreasing. So often we talk about speed, ignoring that sign, and so we could say the speed of the football would be 50.64 feet per second. So the speed is the absolute value of velocity. I know the numbers in this problem weren't so great, but I wanted to try to make it a little bit realistic. Most of the numbers in your textbook are going to be a little bit easier to work with. And so in this lesson, we started talking about some basic differentiation formulas, some basic derivative rules, so that we don't have to go back and use the limit definition every time we want to take a derivative. And so this is the first set of basic differentiation formulas, and in the next lesson, we're going to learn about the product and quotient rules. And so we'll conclude this lesson on basic differentiation formulas here.